Right, everyone, good afternoon. Welcome back to our third lecture for the MSD 780 postgraduate dynamics module. I'm going to jump straight into the mind map, and today we're going to look at the fifth section where we're going to deal with the pendulum rod. Now, before I start with section 5, I perhaps just want to give you an overview of what we're going to look at today and what we looked at in the previous lectures. So for lecture 2, we essentially focused on the undriven pendulum rod, and this was in section 4. So essentially over there, we considered a pendulum rod which is connected to ground simply being actuated due to gravity. So there aren't any physical forces that we apply to the system other than gravity, and therefore it was an undriven system. Our focus in that regard was essentially applying Newton's three laws to evaluate either the joints or the actual motion of the body. And we essentially said that whenever we do these dynamic analyses, we essentially incorporate all three of Newton's laws. So the first law dealing with static equilibrium, the second law essentially relates our forces to the actual kinematics of the system. And you'll remember one of the things that we also said is we follow a systematic approach when we solve these type of problems. We start off with a kinematic analysis where we essentially look at the motion of the system, so the position, velocity, and acceleration analysis. Once we've done this, we can use it as a sort of an input to evaluate the dynamics of the system, and that's where the forces come into play, and more specifically Newton's second law, which simply states that the net forces on a system or a body is equal then to the mass multiplied by the acceleration of the system. And then Newton's third law dealt with kinematic joints. So we said whenever we have a joint, we essentially have a connection between two bodies or a body and ground, and there's going to be some reaction forces that are associated with the system. And we are able to define these reaction forces through Newton's third law. We can also define what we call constraint equations. So whenever we have some sort of a joint, it removes one or two or all three degrees of freedom of a particular body or a connection between bodies. And in that case, we have a number of constraint equations which match the number of degrees of freedom that are removed from the system due to that joint. We essentially went through all of the logistics or the mathematics behind all of the calculations. So one thing that we looked at then for the constraint equations, we started off with a very bare basic constraint equation that we can set up for a revolute joint. We simply equate the two vectors RIP and RJP to one another. So I and J refer to the bodies, P refers to the actual point on that specific body. And once we equate the two vectors to one another, we can now go and look at their derivatives, the first and second order derivatives. And what we noticed over there is we have this submatrix that essentially forms that we can use as a basis for our constraint evaluations. And we call this submatrix or this system of submatrices a Jacobian matrix. And we can also express it then in terms of some sort of a rotated vector and then also an identity matrix or an identity submatrix. We said that the actual Jacobian matrix for the joints, we don't have to know them by heart. We just need to understand that it's an important parameter whenever we do these calculations, and that it's an important matrix that is calculated within our workbench that we're going to look at. So essentially that was, I think, the crux of section 4. Now, for section 5 and what we're going to look at today, we're now going to focus on a driven pendulum rod. So essentially we now have some sort of an input. We can, for example, specify either a constant angular acceleration, a constant angular velocity of the system, and we can say, okay, if I give this as an input, what will the forces be that I measure? And this specifically then deals with the inverse dynamic analysis. So in other words, we give it a motion or a displacement as an input, and we want to measure what the forces are as the output. Of course, a forward dynamic analysis would simply be the vice versa of this, where we give a force as an input and we measure the actual motion of the system as an output. So the idea is we're also going to then jump into Looking at the undriven and driven pendulum rod at the hand of the body coordinate planar multi-body dynamics algorithm, or simply the DAP-BC workbench that we've referred to up to now in our previous 2 lectures. All right, so jumping in then to section 5, we're going to break it up into 2 analyses, and once again these are progressive analyses. So we start off with a kinematic analysis, and then we're going to jump over to the inverse dynamic analysis. Now, starting off with a kinematic analysis, if I scroll up over here, the kinematic analysis, as we now know, is the solution for the coordinates, the velocities, and the accelerations of closed chain systems by solving the constraint equations. Now, when kinematic analysis is considered for a mechanism that has a single degree of freedom, one driver constraint is included in the formulation. So a driver constraint is literally the input that we now give to the system, whether it be a torque or an angular acceleration or an angular velocity that the pendulum rod has to attain. That's some sort of an input parameter that we give. If we don't give that driver constraint as an input, then we sit with the undriven pendulum rod that we looked at in the previous lecture. Now, based on the motion described by the driver, the kinematics of the entire system can then be solved for. And regardless of the choice of the coordinates for a multi-body system with a NDOF degrees of freedom and NV defined coordinates, if NV, so if the number of defined coordinates is greater than the number of degrees of freedom, then there must be NC, which is equal to NV minus NDOF independent constraint equations. So this simply tells us how many constraint equations we need, and this is perhaps a different version of the formulation that we looked at previously. We said we can essentially find the number of degrees of freedom as 3 times the number of bodies that we have in our system minus the number of constraint equations. So this is just a rewritten form of that. NV in this case, which is the number of defined coordinates, is then 3 times the number of bodies that you have, because each body has an X, Y translation coordinates, and it also has a rotation about Z. So that's where the 3 times comes from when we multiply it with the number of bodies. So for a kinematic analysis, we define as many driver constraints as the number of systems degrees of freedom. This general statement of kinematic analysis can then be applied to any system with 1 or more degrees of freedom. Now, for our case of the driven pendulum rod, the number of degrees of freedom is 1. So remember that we have 3 times 1, so 1 body, minus the number of constraints that we impose. So we have a revolute joint over here. Revolute joint limits X and Y translation. So you have 2 constraints. So it's 3 times 1 minus 2, and that's how we end up with this single degree of freedom. And the number of defined coordinates is 3. So that is just the 3 times 1 that gives you the number of defined coordinates. And then we denote our coordinates of the center of mass as well as x1, y1, phi1. So in relation to this, we therefore need a total of 2 independent constraint equations. And this is something that we also set up in the previous lecture, where we essentially looked at if we have the constraint equation that we apply to the revolute joint, it applies to the x and y coordinates, and we just need to manipulate essentially this minus r1a vector in terms of its global center of mass coordinates, and then also some transformation matrix that is multiplied by the local coordinates of the point where the revolute joint is situated. So once again, a lot of mathematics that go into a very simple mechanism that we have over here. It's not even a multi-body mechanism. We're essentially working with a single body mechanism over here. But even in this case, the constraint equations are not very trivial to find. But after we've now defined the constraint equations related to the revolute joint, it also follows that we will have to specify one driver constraint for the driven pendulum rod. And to better understand this, we can look at a general formulation for the kinematic analysis, where Q denotes an array of NV coordinates, then NC position constraints, and NDOF driver constraints are formulated. What we essentially do over here is we break up our constraint equations. So we have constraint equations which are related to joints. This is this first equation that we have over here, and the one that you are now more familiar with from our revolute joint analysis. And then we have this second function that we have over here, and this applies specifically to the driver function that we want to specify on the system. And that is also denoted, if you look at phi in bold, it has a superscript dr. So the dr tells us that we're now working with the driver constraint functions. And we can simply write this as phi superscript dr, which is a function of q, minus f of t, which must be equal to 0. So f of t is going to be the essentially the driving function that we're going to look at. Now for our driven pendulum rod, phi of q has already been defined, and the single driver constraint is then given by this form that we have over here. Now, to understand how we get this, we're sort of jumping the gun a bit at the moment. We're going to look at the actual derivation of this function over here a bit later on when we do a validation of our driven pendulum rod. But just note that in this case, we essentially specify a constant angular acceleration of, I believe it is pi over 2 pi over 60 that we specify, radians per second square, for the pendulum rod. And from there, we can essentially just integrate twice with respect to time, and that's how we end up then with this driver function over here. So everything in brackets over here is then f of t. Now, as we have already seen in Chapter 7, driver constraints are simple functions of one or possibly two coordinates and the parameter time. Now, the first and second time derivatives of equation 12.1 yield the velocity and the acceleration constraints. So the first equation over here should also look familiar from the previous section that we looked at. It's simply taking the time derivative, and what we end up getting in this case is phi dot is equal to our Jacobian matrix D multiplied by Q dot, and this should be equal to 0. So Q dot in this case is simply your x dot 1, y dot 1, phi dot 1, so the velocity vector that we're working with. But now we also have to add this second part in, which pertains specifically to the driver function. So if we derive this, it becomes also dq dot, but now the d Jacobian matrix that we have over here is indicated with a superscript dr. So there's a driver Jacobian matrix and there's a constraint Jacobian matrix that we consider. There is a difference between the two, so just take note of that. And then we simply have minus f dot t, so the time-based derivative of our driver function. And over here, we just have the extended form with regards to the local and global coordinate systems that we define in these matrices over here. And then lastly, if we want to find the second time derivative, it's simply going to be the product rule for the constraint equations. So that's phi double dot is equal to the Jacobian matrix multiplied by Q double dot plus, and then it's the time derivative of the Jacobian matrix multiplied by Q dot, which must be equal to 0. That once again applies to, in our case, the revolute joint. In the case of the driver function that we specify, phi double dot looks more or less the same. So it's once again the product rule that we use to get these first two terms. And then we just have to remember to also derive f dot t again, so that we get f double dot t. Right, and then the coefficient matrix in the velocity and the acceleration equation is square. And this is better realized from this elaborate scheme that we have over here with regards to equation 12.3, specifically for the driven pendulum rod. What you'll notice is the number of rows and the number of columns match up. So we have a 3 by 3 coefficient matrix in this case. Just take note of that as well. Now, with regards to the objective of the kinematic analysis, it is essentially to solve these algebraic equations for the coordinates, velocities, and accelerations for a specified time period at delta t time intervals. What this essentially tells us is that whenever we solve these problems, it's not going to be a matter of an analytical solution that we simply get. We're going to have some sort of an iterative solver that we apply. And this is better illustrated through algorithm K, which essentially tells us how we solve these problems. And we sweep the time parameter from t equal to 0 to tn, so the total time range that we're working over, by increments of delta t, so a time step that we specify. At each time step, we perform the following steps. So we solve equation 1 so that we get the positions or the coordinates. Then we solve equation 12.2 to get the velocities, equation 12.3 to get the accelerations, and then we can compute the coordinates, velocity, and acceleration of any points of interest once we have these generalized vectors defined. Now, algorithm K can be applied to any closed chain system regardless of whether the constraints are formulated in the body coordinates, the vectorial or the joint coordinates, or any other formulations. For our continuing discussion in this chapter, we show some examples that are formulated with the classical vectorial method. And that we will look at that in a moment, just with regards to example 12.1 as well. If you're more interested in looking at algorithm K and how it's solved iteratively, you can have a look at this example 12.1. Not too interested in the actual algorithm, just understanding that we have some sort of an iterative solver that's going to assist us when we start solving these type of problems in our workbench. So moving on to section 12.1.1, we now deal with the solution procedures and the methods that we can use to solve these problems. So a kinematic analysis requires solving the kinematic and the driver constraints at a given time t equal to t superscript I, so at the ith time step, for the coordinates, velocities, and accelerations. The position constraints are in general non-linear algebraic equations, but the velocity and acceleration constraints are linear in the velocities and accelerations, respectively. Now, whether we solve linear or non-linear equations, we may consider two possible arrangements for the equations, and this is better illustrated through a fairly simple example that we have over here. So we can consider a simple set of two equations, so a linear set of equations that we have available in three unknowns. So we have x plus 2y minus z is equal to 2, 2x minus y plus z is equal to 3. In the case of our driven pendulum rod, we can rewrite this as saying x1 is equal to, and then we have this combination of the transformation matrix with the local coordinates. In this case, we know what the local coordinate of point A on body 1 is with regards to the xi and eta directions. So we have that available. What we don't know is the value of x1, y1, and then phi1 as well. So essentially the translational coordinates of body 1 as well as the actual angle of body 1. Now, if we assume that the value of one of the unknowns is given, in the case of equation A, we can assume that z is equal to 3. For our driven pendulum rod, this will then change to phi1 as a function of time is equal to this function that we have over here. And this matches up with what we saw, I think it was in this part over here. So phi1 as a function of time is essentially given. That is an input angular acceleration, which we simply derive to get this input value over here, which we can essentially consider to be the same as a constant as what we had over here in equation B. Now, equation A may be considered as two kinematic constraints, and equation B may be viewed as a driver expression without the presence of the time variable. And this is now where we jump into the two arrangements of how we can actually solve these problems. The first arrangement says that the value of z is obtained from equation B, and we simply substitute this into equation A. So we substitute in to get x plus 2y minus 3 is equal to 2. If we take the minus 3 over, it becomes x plus 2y is equal to 5. And in the case of the second equation, if we substitute z in, we get 2x minus y is equal to 0. And just to make it a bit easier from a computational perspective as well to view this type of problem, we can simply go and write it in matrix form. So we have a coefficient matrix multiplied by a variable vector, which is going to give us our solution vector on the right-hand side. So these equations are solved to determine the unknowns to be x equal to 1 and y equal to 2. And this particular arrangement is then called the coordinate partitioning method, or the CP method. For our driven pendulum rod at time t, we can obtain phi1 as a function of time, and we can then solve the two equations accordingly. And this is essentially what we're going to end up with over here. So we know what the values of the local coordinates, and we know what phi1 as a function of time is as well. So essentially x1 and y1 as a function of time reduces to these equations that we have available over here. All right, so that's one method where we directly substitute in the known value. This is known as the coordinate partitioning method. Now we can look at the second arrangement, which simply says that we can now combine equations A and B, and they are considered simultaneously to form three equations in three unknowns. So we expect a unique solution then. And this simply means that our coefficient matrix now grows to a 3 by 3 matrix if we look at our x, y, z variables that we have in equations A and B. And we can once again solve this problem simultaneously to obtain x equal to 1, y equal to 2, and z equal to 3. Just perhaps a quick note over here. What I noticed is they say 3, a value of 3 over here in the coefficient matrix. This should, I think, be 1 because you're working with z equal to 3. So the coefficient of z is equal to 1. So this should be 0, 0, 1 in this last row. So just take note of that error over there as well. But in any case, the methodology remains the same. You essentially just combine your equations together, and we call this arrangement then an appended constraint, or AC method. In the case of our pendulum rod, we simply write our three equations in this form that we have over here. And you'll notice all that we do is we essentially keep the right-hand side as a 0 vector, and we carry over everything to the left-hand side, so we end up with this form over here. And then we can do some reduction to end up with these three equations that we have over here. All right, so although the arrangements are not very different, from the programming and computational points of view, there are advantages and disadvantages associated with each of these. And you can also have a look at example 12.2, but to essentially just summarize what the advantages and disadvantages are. In the case of the coordinate partitioning method, the number of equations and hence the number of unknowns is smaller than those in the AC method. So therefore, the computational effort with the CP method is less than the AC method. However, for developing a general purpose kinematic analysis program, the programming effort that the AC method requires is much less than that of the CP method. And this is due to the fact that in the appended method, the constraint equations keep their original forms. We do not need to split a set of equations or do any manipulation of the equations into the known and unknown parts and move the known part to the right-hand side. We don't have to worry about that. We essentially use them in their native form. Another important point is that in problems with a large number of equations and coordinates, appending one or two driver equations to the original set will not make much difference in the computation time. And therefore, in most problems, we'd rather adopt the AC arrangement so that we have a bit more generality and a bit more ease of access when performing multi-body dynamics. Okay, so then the next point deals with the velocity and acceleration constraints. Whether we arrange them for the CP or the AC method, they are respectively linear in the velocities and accelerations. And solving these equations for the velocities and accelerations then requires solving simultaneous linear algebraic equations in this form over here, AX equal to C. And this is a solution to a set of simultaneous linear algebraic equations using the backslash operator in MATLAB. Now, those of you who've undertaken the numerical methods postgraduate course as well might remember the backslash operator and the type of elimination procedures that go into that when we do those operations in MATLAB. We're not too interested in the actual numerical method, but we know that this is a fairly good solver to find the solution vector x. However, another useful method that we can perhaps use for solving a set of linear algebraic equations is called LU factorization. So what we essentially do over there is we break up our coefficient matrix into a lower matrix, so a matrix that essentially has most of its non-zero elements below the diagonal, and then a U or an upper matrix with most of the elements or the non-zero elements being in the upper diagonal. And this is then discussed in Appendix A if you're more interested in the actual factorization scheme in this case. And this method is also useful in identifying any redundant equations in case the coefficient matrix A is singular in nature. The kinematic position constraints, in contrast to the velocity and acceleration constraints, are nonlinear algebraic equations. Now, as it will be seen in section 12.1.2, nonlinear algebraic equations can be approximated as linear algebraic equations and once again solved iteratively for the unknowns. So we see once again that there's an iterative component whenever we solve these problems. All right, before I go on to section 12.1.2, are there any questions so far with regards to the formulations? All right, everything seems quiet at the moment. So in that case, I'm then going to continue on to nonlinear algebraic equations and the method that's used to solve them. Now, one frequently occurring problem in scientific work is to find the roots of one or a set of nonlinear algebraic equations that have this form over here, phi as a function of q being equal to 0. Now, kinematic analysis of mechanical systems is one example for which the solution of positive constraints in the form of equation 12.7 is required. As shown in the planar multibody dynamics textbook as well, for example 5.2, the function fsolve in MATLAB can easily find the roots of such nonlinear functions for us. Now, to learn how the zeros of nonlinear algebraic equations are determined, in this section we will discuss the Newton-Raphson methods. This is an iterative solver that finds the roots to a nonlinear algebraic equation or a set of nonlinear algebraic equations. And we describe this process first for a single equation, and then we can move on to multiple algebraic equations, nonlinear in nature, that have to be solved at the same time. So firstly, for one equation, we can consider the following nonlinear equation in one unknown. So phi q is equal to 0. Then the Newton-Raphson iteration for solving this single equation is stated in this algorithm over here. So we essentially start with an assumption or an initial guess for whatever our root value will be. We can then evaluate the actual function, phi superscript I, so the ith function evaluation, which is then a function of the actual initial estimate that we made or initial guess that we made for the root. And then we can apply some sort of a tolerance to that function evaluation. So if the function evaluation is smaller than or equal to whatever the tolerance is, let's say, for example, 10 to the power of minus 4, then q superscript I is the solution. So it's essentially close enough to 0 that we can accept it as a solution. Otherwise, we need to go and evaluate the derivative, d superscript I. So this is simply d phi dq. And we can use this to update our guess. So we calculate delta q, which is then that function evaluation divided by the derivative, and we improve the estimated solution as qi plus delta qi, which is now the next guess that we, or the next calculated guess essentially that we have for our root. And then we can return to step 2, and we keep iterating until we actually find a function evaluation or a function value that is below this tolerance that we specify. And over here they also state that epsilon is a small number that we accept as 0. So something like 10 to the power of negative 4 or negative 6 we can accept as being close enough to 0 that we can use that iterated solution that we found as the final solution. So we can use the Newton-Raphson method to then find the roots of this equation over here. This is a fairly simple equation to find as well. You can go ahead and essentially apply this algorithm in MATLAB or Octave if you want to, but I'm essentially just going to give you a breakdown of what the solution gave us as an output. So if we first look at the function, we need to perhaps go and find the derivative firstly. So df dx is simply this equation over here, 3x squared minus 6x minus 10. And now we can start iterating and updating our steps based on the derivative values. Since this process is iterative, the program asks for an estimate or an initial guess for the unknown x to start the iteration. And entering a value starts the Newton-Raphson process. For example, if we enter 10, the iteration will converge to x equal to 8. We may report the intermediate values of x and fx during the process in order to have a better understanding for the convergence of the algorithm. Now, once again, from a numerical methods perspective, it's always a good idea to essentially see what happens at each iteration. And what you want to see with this type of iterative solver is a sort of convergence, or that your estimate for the solution essentially plateaus towards the end of the iterations. An estimate of 10 for x takes 5 iterations to converge. And if we now look at where we started, so 10 is over here, we can clearly see where the roots are plotted. So according to this setup, the Newton-Raphson scheme seems to approach the closest possible solution that it can find. In this case, it's going to be x equal to 8. If I were to perhaps define, let's say, x equal to 5, it might have converged to, I believe this might be 2 or 3, which is the root, one of the other roots that the function has. If I specify x equal to minus 5 as my initial guess, it might converge over here to minus 6. Right, so since we started with an estimate of x equal to 10, we converge to the solution closest to the estimate. If we start with a different initial estimate, we might find the other solutions as well. So our initial guess has an impact on the effectiveness and the number of iterations it will take, the actual solution that we get at the end. All of those parameters will be affected by our initial estimate. Now, the Newton-Raphson method, when it works, is very efficient, but it may converge to an unwanted solution if the initial estimate is not close to the desired solution. It is also possible for the iterations to diverge. Therefore, it is essential to terminate the process after a finite number of iterations. So typically what we would do to algorithm NR1, we have one of the conditions which says if the function value is smaller than a tolerance, we accept it as the solution. But we can also state another condition where we say if the maximum number of iterations, let's say it's 20 or 30, are reached, or if the maximum number of iterations is reached, then terminate the algorithm and plot out what actually happens to the value of the variable at each iteration. And then we can see whether it diverges, whether it converges, whether it needs a few extra iterations to converge to the solution that we need, or whether our tolerance that we specified is simply too small and the Newton-Raphson method struggles to find a solution. Right, so that was for a single equation. Now, once we deal with multiple equations, we need to consider n nonlinear algebraic equations in n unknowns. So previously, we didn't have this phi as a function of q equal to 0 as bold. In this case, it is now bolded out, so we're working with vectors and matrices in this case. The Newton-Raphson algorithm for n equations is the n-dimensional version of algorithm NR1. And in the algorithm, we now need the Jacobian matrix. So the Jacobian matrix is essentially the multi-dimensional version of the derivative that we considered previously. And an algorithm for this process is then stated over here in algorithm NRN. So you can go through this, but you'll see the crux of the matter essentially remain the same, where we previously just considered the single function value. In this case, we now have a norm that we consider which must be smaller than a tolerance. So the array phi I is known as the array of residuals, which corresponds to the violation in the equations of the constraint. And the term norm phi I smaller than or equal to epsilon is then the norm of the residuals. If this term is then smaller than the specified tolerance epsilon, then every residual is small enough to actually stop the iteration. So this norm is essentially a combination of all of the errors that we make across the equations when we want to find their roots. Okay, so that is then the methods that we apply to the kinematic analysis. We can then jump into section 12.2, which then deals with the actual inverse dynamic analysis. So now that we've constructed the equations, we know what the iterative solvers are that we need for the kinematic analysis. We perform those calculations, and now we move on to the actual inverse dynamic analysis that we're going to perform. Now, the equations of motion for a mechanical system represent the relationship between the forces that act on the system and its motion. So once again, we refer back to Newton's second law, which says that the forces are directly proportional to the mass and the acceleration of the system. If a specified motion of a mechanical system is sought and some of the applied forces and moments are known, it could be possible to determine the remaining forces and moments that cause that particular motion. And when the desired motion is known and the objective is to find the unknown forces and torques, the process is referred to as inverse dynamic analysis. Inverse dynamics is an extension of the kinematic analysis in which the reaction forces and the unknown forces or torques associated with the driver constraints are determined, and the fundamental process for inverse dynamic analysis is the same regardless of the method used to formulate a problem. Furthermore, inverse dynamic analysis of a multi-body system requires a kinematic analysis to be performed first, and we know this now from the previous examples that we also looked at. We first look at the motion and then we consider the forces, and this is simply to determine the coordinates, the velocities, and accelerations before we go any further. Now, if Q does not contain the complete kinematics of all the bodies in a system, in the case of a vectorial formulation, for example, the body coordinate arrays of C, C dot, and C double dot must be determined prior to performing a force analysis. And the equations of motion for a system based on either the body coordinates from equation 755 or free body diagram method can be formed in this regard that we have over here. So MC double dot, which is equal to our applied forces vector. So this is something like the gravitational effect. Plus, then we have the constraint Jacobian, the transpose of that multiplied by the Lagrange multiplier. So everything that has to do with the actual kinematic joints in the system. And now we have this extra term over here, which now compensates for the driver constraints that we have in our system. So the driver Jacobian matrix, its transpose multiplied by the driver Lagrange multipliers. Now, the Jacobian and Lagrange multipliers associated with the driver constraints are included but separated from those of the kinematic joints. In the case of our pendulum rod, it follows that we have this form over here. This is essentially what we got previously. So we have applied forces, and then we have our not our driver Jacobian, we have our constraint Jacobian multiplied by the Lagrange multipliers as well. Which is then going to form the second part that we have. Now, these equations can also then be rearranged once again in matrix form. So we have a matrix that consists of a Jacobian submatrix for the constraints or the kinematic joints, and then for the driver constraints as well, multiplied by a Lagrange vector, which is once again broken up into the kinematic joint Lagrange multipliers and the driver Lagrange multipliers as well. And this must simply be equal to MC double dot minus our applied forces vector that we have. In the case of our driven pendulum rod, equation 1211 can then be written in this form that we have over here. And since the coordinates, velocities, and accelerations are known, the coefficient matrix and all the terms on the right-hand side can numerically be evaluated. So this is essentially constant vectors that we're going to get on the right-hand side. Then the equations are solved as a set of linear algebraic equations for the Lagrange multipliers. The results for d prime lambda provide the joint reaction forces and torques, and then d driver prime lambda driver yields the forces or torques associated with the driver motors. For our pendulum rod, the joint reaction forces and torques are given in this form over here. And for our driven pendulum rod, the torque associated with the driver motor is simply stipulated in this form over here. So since we have a rotational driver motor, we expect there to be some sort of a Lagrange torque that's going to form, and that's why we have a 0, 0, 1 vector over here, which is multiplied by the actual Lagrange multiplier value of lambda 3. All right, so just the last point as well. Algorithm ID1 can also be used in the case if we don't have Q which is not equal to C. We can simply determine C dot and C double dot. This is, I think, a reduced version of the actual coordinate vectors that we have over here. But this is essentially the method that we follow. We construct a mass matrix and the array of applied forces. We construct a Jacobian matrix for the kinematic joints, the Jacobian matrix for any driver constraints, and then we can solve equation 1211 for the Lagrange multipliers. And the solution to equation 1211 provides the results for all Lagrange multipliers, which relates back to our actual dynamics or the forces that are applied in the system. Okay, so that was quite an elaborate mathematical study of everything that's now going into the DAP-BC workbench. Yeah, so perhaps before I continue, any questions at this stage? Right, I think we're still good. So in that case, we can now get to the actual fun part of the dynamics module. I think up to now we focused a lot on the underlying principles and the mathematics, and it is important to understand those, but at the end of the day, we also want to be able to apply them in whatever workbench we make available. So in order to do this, we're going to use the DAP-BC workbench that has been uploaded to ClickUp, and more specifically, I think the DAP-BC 12 workbench that is available. So that is the latest revision essentially of the workbench. It gives us a bit more flexibility with regards to how we can specify certain user functions. But to perhaps show you how we're going to access it and use it, I'm now going to jump into Octave. You can also use MATLAB. What I just found is that Octave tends to run some of the scripts a bit faster. So do consider using Octave when you do these kinematic and dynamic analyses using DAP-BC. But in any case, so if it's your first time working with Octave, you'll essentially download version 10.2.0, and you're going to access Octave 10.2.0 GUI. So this is the actual user interface of Octave that we want to use. Right, so opening this up, you will probably be greeted with something similar to this command window that you see over here. So on the left-hand side and at the top, you have your file browser. In the middle, you have your workspace. So this is whenever you specify some sort of a variable, it will be stored in this workspace, and you can actually go and look at what the properties are, the dimensions, the class, the values, the attributes, and the actual name that you assign to those variables. And then at the bottom, you'll have your command history. So this is just basically a setup of all of the commands that you have run in the command window before. All right, so to now access the DAP-BC workbench, you can simply go and browse to the specific folder where it's stored in my case, I'm just going to go to MSD, and you'll see DAP BC workbench material, and then you'll see this DAP BC 12 2022 file over here. So you're going to double click on that, and once you've done that, you just click on choose. And now you're essentially in the main DAP BC folder, and this is the folder that you have to work in whenever you set up or change any scripts under the models folder. Essentially, this is where your formulation and models folder and all of the post-processing comes together. So make sure that you work in this main folder. Now, once we've done that, you can go and expand over here the models folder, and you'll see there's a bunch of different models that we have available. In our case, we want to start with PR_B. So this is the undriven pendulum rod that we're first going to look at. We essentially just want to get an idea of what are the underlying dynamics when we don't have any forces or any kinematics or prescribed displacements for our pendulum rod. So for PR_B, you can once again expand it, and then you'll see there are a bunch of .m files that you have over here. And these are the files that we are essentially going to change. They are function files. Depending on the number of bodies that we have, the number of points, joints, forces, all those kind of things, we can go and update them in these specific input files, and we can run the total script accordingly. All right, so before I get into that, I'm just quickly going to show you the hand calculation that I did for the undriven pendulum rod, just so that we can get an idea of what we're working with. Still under the PR_B folder, I'm just going to use my file explorer to actually get over here to the undriven pendulum rod kinetics PDF document that you have over here. So in this case, if I look at the calculations and what is given to me, I can quickly do a dynamic analysis for the initial condition just to see what the actual forces in the system are, so that I can later compare this to the results that I'm going to get from the DAP BC workbench. All right, so in my case, theta is defined as the vertical angle that I have over here for the pendulum rod. You might remember previously we said phi 1 is equal to, I believe it was minus 30 degrees. So this theta is essentially the same. It's just a bit easier to evaluate the forces, the reaction forces using this angle theta in this case. But in any case, if I now go and apply a moment equilibrium about point A, I'm going to write sigma MA is equal to IA theta double dot. So this is my mass moment of inertia about point A. And then I can go and do the moment equilibrium calculation. I can see that if I'm situated at point A, the only force that is actually going to cause a moment arm in this case is this mg sine theta, so this component of the weight that I have available. And this is then the perpendicular component multiplied by the actual moment arm, which is L over 2. And this is the net moment that I calculate on the left-hand side. For the right-hand side, I've now expanded my mass moment of inertia as 1 over 3 ml squared, and then I just multiply by the angular acceleration of the body, which is theta double dot. So how did I get this mass moment of inertia? Well, if you do a quick Google search, you can actually have a look at the mass moment of inertia formula tables that you have at your disposal. So if you go to, let's go to images, and we can perhaps use, let's say, this one. Right, so depending on the actual geometry that you have, your mass moment of inertia will differ. You might also have different axes about which you want to find the moment of inertia. In our case, we have a pendulum rod, so we can assume we're working with a long, thin rod, but its moment of inertia is now taken about point A, because I'm doing a moment equilibrium calculation about point A. Point A is one of the endpoints of the pendulum rod. So I'm not going to use this function over here, this 1 over 12 ml squared, because that's for the case where I'm working around the center of gravity. If I'm working at one of the endpoints, my mass moments of inertia is 1 over 3 ml squared. And this is essentially what I plug into this function over here. And then I can go and rewrite the system so that I get theta double dot is equal to minus 3g sine theta divided by 2L. If I plug in all of the constants that I have at my disposal, I get that my angular acceleration at the initial orientation of the pendulum rod is this minus 21.24 radians per second squared. Okay, so then I can also do a simple calculation for the translational forces that I have, so the xi eta forces that I have, and you can run through that on your own time as well. But essentially what you're going to end up with are the values for n xi, n eta. So if I substitute that in, I get 4.25 newtons, 9.81 newtons. So now I just need to remember that this is in the local coordinate system of the pendulum rod. I'm not really interested in local coordinates or local coordinate based forces. I'd rather want to relate them to the global coordinate system, so the XY coordinate system, because this is how DAP-BC is going to give me the outputs as well. The Lagrange multipliers, the reaction forces, the torques, all those kind of things will be related to the global coordinate system. And to do that, I can simply use, once again, a method of transformation to go from local to global coordinates. And if I calculate nx and ny, I get these values minus 6.37 newtons and 8.58 newtons. The signs in this case aren't too important. My formulation of, well, how I specify the revolute joint in DAP-BC might cause the signs to change. So I might have 6.37 minus 8.58, something like that, or a combination of the signs that have been changed. The idea is just that I get essentially the same magnitude or something close to the magnitude that I'm going to get in DAP-BC. Right, so now with that being said, I also just want to open up the actual pendulum rod schematic that we have over here. So just to remind you, when we work with the pendulum rod, we have a known length. We also have a known angle that we're going to start off with, which is minus 30 degrees. And we have a local coordinate system, which is placed at the center of mass of the pendulum rod, which coincides with the geometric center in this case. So xi is orientated in line with the, with the length of the pendulum rod, and eta will then be perpendicular to the rod. The xy, or the global coordinate system, is on ground, and it's also placed at the revolute joint on ground. And then I have points 1 and 2. So point 1 is the point that is on ground for the revolute joint, and point 2 is coincides with point 1, but it's now on body 1. So remember, when I have a kinematic or a revolute joint, those two, I essentially need 2 points that lie on the 2 bodies that have to coincide with one another to form the revolute joint. So that's why I have points 1 and 2 coinciding over here. And then point 3 I can simply use as a reference point in this case. Right, so then I can go ahead and essentially open up all of the function files that I have over here. So I'm just double clicking on each of these files, and then we can essentially run through them. Now I'm going to start off with in-bodies, and to perhaps assist me in describing what happens in each of these files, I'm just going to open up the DAP-BC user manual. You'll also have this available on ClickUp, so you can use this to see what your inputs and outputs have to be when you set up your multi-body mechanisms. All right, so for the case of in-bodies, I can essentially quickly run through that on my own. With regards to defining a body, what I have to always start off with is calling the specific body a body structure. So in this case, I have B1. So B1 will be the pendulum rod, is equal to body underscore struct. So this makes sure that DAP-BC initializes all of these properties that I give over here as a body structure. So all of these properties form part of a structure. Once I've specified this first line, then I can specify the mass of the system. So that would be B1.m, and that is equal to 2.0. So that's the kilograms, the mass in kilograms of the pendulum rod. Then I also specify the moment of inertia of the rod, which is equal to 0.06. And this moment of inertia is always specified about the center of mass. So if we go back to the formulations over here, in this case, I'm actually going to use this long, thin rod, its mass moment of inertia about the center of mass. So that's why I use 1/12 ml squared. If you work that out on your calculator, you should get something close to 0.06 based on the length of 0.6 meters that was given to us. You could have also typed in over here, well, you could have essentially said just say 1/12 times B1.m times, and we know it's L squared, so it's 0.6 squared. And it would have also calculated that value. But for simplicity's sake, at the moment, we're just going to leave it 0.06. I've calculated this with my calculator, and I just plug in the value over here. Then B1.r is the next property that I have to define. And this is essentially the location of the center of mass of body 1. Now, if I go back to the pendulum rod that I have over here, I know I'm working with -30 degrees. I know the rod length is 0.6 meters, so I can use that and trigonometrically find the location of the center of mass. And that's why I got the 0.259808. So it's in the positive x direction, and then below the x-axis, we have the center of mass. So that means our y value needs to be negative. And if I calculate that, it should give me 0.3 sine 30 degrees, which is 0.15 meters. And this is indeed what I get over here, just with a negative sign because it's below the x-axis. Then I also have B1.p, so that is the initial orientation of body 1, or the pendulum rod. And this has to be given in radians. So where I had -30 degrees, if I relate this to radians, it's simply -pi/6. So I plug that in over here. Then I also define B1.r_d. So this is the initial velocity of the pendulum rod. And I simply give this as a 0, 0 vector in this case. And that essentially tells me that the pendulum rod is starting from rest. I could have also simply commented this out. So if I just add a percentage sign in front of this, if I don't specify it, that BC will use the default value of 0, 0 in any case. But if I really want to, I can still place it in. Now, to give you an idea of the default values that we work with, we can also go to the in-bodies file that we have over here. So in the user manual, it essentially tells you what all of the properties are that you have to specify for each body. So we now know we specify the mass, the moment of inertia, the x and y coordinates, the angle phi, so the angle of the body, r_d, which is the time derivative of x and y, or simply the velocity of the body, and p_d, which is then the rotational velocity of the body as well. And these are essentially all of the default values. So if I don't specify any of these values, that BC will use, for mass, it will use 1 kilogram, for moment of inertia, 1 kilogram meter squared. For R, it will use 0, 0, and so forth. So in our case, you might see that we didn't specify p_d. We didn't say over here b1.p_d equal to 0. So that BC will in any case assume that the starting angular velocity is 0. All right, but this is essentially all of the properties that I then plug in for my pendulum rod body. And then at the end, I just have to group all of the bodies together in this bodies list that I have available. So bodies in this case is equal to B1 if I perhaps had a second body. So let's say two pendulum rods which were linked to one another. Then this would be B1 semicolon B2 for three bodies, semicolon B3, and so forth. Now it's also just important to notice that when you specify these vectors over here, when you have some sort of an X or Y coordinate that you have to give in tandem with one another, we use a semicolon as a separator between the X and Y values. And this just makes sure that we're working with a column vector and the DAP BC is able to properly manipulate all of these vectors that you give as input. Right, so this is then in bodies. Then next we can look at in points. And this is now where we start looking at the actual points which are going to be combined with one another or coincide with one another for revolute joints, just to make sure that we have proper connectivity between the bodies. Now, looking back at our pendulum rod, we said points 1 and 2 are situated over here, and then point 3 is situated at the other end of the pendulum rod. Point 1 is on ground, point 2 is on body 1, but they coincide with one another. And if I then look at the user manual and I go down to in point, you'll see that whenever I specify a point structure, I need to give a body index. So on which body is the point located? And then SP local is the body fixed or the local coordinates of the point that I specify. Now looking back at the pendulum rod, my local coordinate system is situated over here in the xi eta directions. So if I had to specify point 2, which is on body 1, it will be in the negative xi direction. So it would be minus 0.3, and it's in line with the xi axis. So its eta value is 0. So my SP local vector will essentially be minus 0.30. But let's perhaps look at it from the beginning, and let's start with point 1. So P1 is initialized as a point structure, so point underscore struct. P1.B index is then the body index. And remember, point 1 is specified on ground. We don't have to specify body, or we don't have to specify ground as a body. That BC automatically detects ground as body 0. So whenever I have a point that is situated on ground, the body index in that case will be 0. And that's why I use P1.B index equal to 0. And then the last entry over here is P1.SP local is equal to 0, 0. And this is simply because when I work on with ground, its local coordinate system is essentially the global coordinate system. So I use the XY coordinate system in that case. And point 1 is at the origin of the global coordinate system, and that's why it's a 0, 0 vector that I have over there. Point 2, however, is situated on body 1 or the pendulum rod. So I first initialize it as a point structure, and then P2.body index or B index is equal to 1. So remember that I'm working now with the indices as well. So if I go back to in bodies, index 1 in this list that I have over here, this is the first index. So index 1 is indeed body 1. And I can simply use B index equal to 1 in this case. And then I just give its local coordinates with respect to the center of mass of the pendulum rod, minus 0.3 and 0. And then lastly, I have point 3. So if I look at this, point 3 is now situated on the opposite side of the pendulum rod, so in the positive xi direction. So its local coordinate systems, it's still on body 1, its local coordinate systems will be 0.3 and 0. And I simply specify it accordingly. And as I then did with in bodies, I then go to in point, or I essentially create a list at the end to group all of the points together that I specified. And that is why I now say P1, semicolon, P2, semicolon, P3, and so forth. Right, so once I'm happy with that, then I can go over to the in joints file as well. And this is now where I actually define the connections between the bodies, the kinematic joints that I have to set up. To better understand this, I can head back to my user manual. And if I scroll down to the in joint part, which is over here, this is essentially all of the properties that are allocated to the joint structure. However, the type of joint that I have will govern which of these properties I need to define. So in my case, I'm working with a revolute joint. If I go down to this table over here, you'll see that if I specify the type as a revolute joint, I need to give it two inputs. I need to give it an IP index as input and a JP index as another input. So what are these two inputs? These are simply the I and J points that are coinciding with one another on the two bodies that are connected via revolute joints. If I look back at the pendulum rod over here, points 1 and 2 are the 2 points that coincide with one another. So I essentially need to understand two things. I first need to specify that I'm working with a revolute joint. And secondly, because I'm working with a revolute joint, I'm going to specify points 1 and 2 as the two coinciding points that form the joint. So going back over here, J1 is equal to joint struct. So I initialize it as a joint structure. Then J1.type is equal to rev. So this is the shorthand for the revolute joint. And now because I specified this, now I can say J1.IP index is 1, J1.JP index is equal to 2. So how do I get this? Points 1 and 2 are the coinciding points. So if I look at my points list over here, indices 1 and 2 are the I and J points that I use. So I extract them essentially in this in joint, and I say those are the 2 points that are connected to one another. And then lastly, I simply have to group all of my joints together in its list. And in this case, I have a single joint. So it's just going to be a single value array that I specify over here as J1. Right, once I'm happy with that, I can then move over to in forces as well. Now remember that this is an undriven pendulum rod. I'm not specifying any forces on the system. I essentially just want to see what happens to the pendulum rod under the effects of weight. So if I go to in forces, I of course need to specify that weight needs to be activated for this simulation. And once again, in the user manual, if I go to in forces, which I believe was over here to the top, you'll see I have a set of different forces that I can once again use. For gravitational force, my type is simply defined as weight. For a point-to-point spring damper actuator, its type is defined as PTP. Rotational spring damper actuator is then ROT-SDA. If I want a constant force acting on a system described in the body fixed frame, so in the local coordinate system of the body, then its type is F local. A constant force in the global coordinate frame or XY frame is then a type F. Constant torque will be type T, and then if I have some user supplied force, the type of force will be user, and I'm also going to create another input file called user_force, and we'll look at that in the upcoming lectures for our application examples. For now, we just need to understand that if I specify weight, then two of the entries that I can also specify is gravity and WGT. So if I'm not mistaken, I think they give a breakdown over here of the default value. So if I choose not to specify gravity and WGT for the weight force that I set up, then it will in any case use the gravitational constant as 9.81 meter per second square. And WGT is the direction in which the gravity is then going to act. And it's a common practice to simply use the y-axis, the negative y-axis as the direction of gravity. And that's why it's 0, -1 in this case. So in my case, I don't really have to worry too much about specify gravity and WGT. I can simply go with the default values that are in any case built into that PC. So S1 is a force structure. S1.type is then equal to weight, and I group all the forces, in this case the single weight force, together in my forces list over here. Right, so once that is done, I can also have a look at infuncts. So this is simply where I will be specifying any driver constraints that I have on the system, kinematic driver constraints in that regard. In this case, I don't specify any functions on the system because it's an undriven pendulum rod, so it's simply an open list in this case. And then I believe the last or the second last input file that we have to consider is in U vectors. In this case, you'll notice U vectors is also an empty list. The reason for that is we don't have any translational joints that we specify. Whenever we start specifying translational joints, we're going to start setting up unit vectors, and this is where in U vectors is going to become important. However, for our application in the undriven pendulum rod, our single joint is a revolute joint. We don't have to worry about translational joints. We don't have to worry about unit vectors, so we leave the U vectors list as an open list. And then lastly, we can also look at inanimate. So for inanimate, we can essentially specify any points over here that are simply animation points. So points that don't really contribute to forming joints between bodies or have any significance in the actual dynamic analysis of the system. In our case, we didn't really consider any such points, so we can leave points underscore anim as an open list. However, one thing that is important in this case is the minimum and maximum bounds that we specify on our graph. Now, if we look back at our pendulum rod, we remember that the length of this rod was 0.6 meters, and the XY coordinate system is situated at the revolute joint. So the furthest that I suspect this pendulum rod to swing is 0.6 meters to the right. We know that it's not actually going to swing up to there, but we essentially just want to specify a bound that is large enough to accommodate 0.6 meters on both sides. So in the X direction, my bounds will be, well, I can use minus 0.6 to 0.6, or I can go a bit bigger. So in this case, I'll make it minus 1 to 1. And then in the Y direction, I don't expect the pendulum rod to swing upward because it's only affected by gravity. It will essentially keep oscillating below the x-axis. So I can perhaps use 0.2 as a maximum y value, and then I can use, let's say, minus 1 for the lower bound on the y values, or the graph that I want to plot out. And this is essentially what I specify over here. My bounds on x is minus 1 to 1, and my bounds on y is minus 1 to 0.2. That gives me a large enough workspace to actually see what happens during the simulation. Okay, so once I'm happy with all of that, I just want to move this out of the way as well. We can go to the command window, and you'll notice I'm still working in my main folder over here. But before I start doing any calculations now, what I usually like to do is to first make sure I clear the workspace so that I don't have any residual variables that will influence my analysis. So I'm just going to type in clear all, and this will ensure that this workspace over here doesn't have anything populated in it. Semicolon, then I can also type in close all. So close all makes sure that I don't have any graphs in the background that are still open. If there are any graphs open, it will close those graphs. And then lastly, I can say CLC. So CLC will then clear the command window, and this is the command window that I'm typing in now. So if I hit enter, then I start with a blank command window, blank workspace, and I can now run my analysis. All right, so to start off the analysis, I'm going to type in the keyword DAP. and I'm going to hit enter. And then I'm asked which folder contains the model. So if I look at my models folder, I now worked with PR_B. That is the undriven pendulum rod. So I want to type in over here PR_B, and I'm going to hit enter again. And now the system asks me, do I want to correct the initial conditions? So initial condition correction is something that we're going to look at later on as well. Essentially, it's a method in the DAB-BC workbench where it connects the various bodies more robustly to one another. So if I perhaps have some truncated values that essentially cause my system to have discontinuities or connections that are broken, if I say initial condition correction, DAB-BC will essentially look at those inaccuracies, reevaluate them, and make sure that all of the bodies are interconnected to one another as they should be. So it's always good practice to simply say over here y, so yes. And I can also then validate that the coordinates that I gave in for the center of mass of the pendulum rod are indeed correct. In this case, x is 0.259808. That is indeed what I specified under in bodies. Y is minus 0.15, also the same as in bodies, and then phi is now expressed in degrees as minus 30. You'll remember we specified it as minus pi over 6 in our input file, so this does match up indeed. And then we also know the pendulum rod starts from rest, so x dot, y dot, phi dot are all 0, and this correlates with my expectations. All right, so next up, it then asks for a final time. So for how long do I essentially want to run this simulation? I'm going to type in 3, so for 3 seconds. And then I need to give it a reporting time step. With regards to this, it's always good practice to start with a coarse reporting time step to look at the animation. And if you're happy with the animation results, then you can go finer with your time step to get better post-processing results. So I'm going to start off with 0.1. That will give me 30 time steps. Once I've done this, I simply hit enter, and the system prints out a bunch of function evaluation criteria over here. It tells me that the number of function evaluations it required to solve this problem is 603. And now I'm interested in what the actual animation looks like, so I'm just going to type in anim. I'm going to hit enter, and now it's going to bring up this graph that I have over here. And on the command window, it then says I need to press a key to continue. So if I press, let's say, for example, G on my keyboard, we can now see that it simulates the multi-body mechanism accordingly. All right, so my animation does seem to match up with my expectations. I don't expect the pendulum rod to go above the x-axis. I expect it to essentially oscillate in the lower region or below the x-axis. So if I'm happy with that, I can go ahead, I can close the animation, and now I can start looking at some of the post-processing results. So to do this, I essentially type in post, and what the system now does is it groups together all of the results that it found from its dynamic analysis into suitable arrays. To better understand these arrays, we go back to our user manual, and we can scroll down to the post-processing part, which I believe was over here. All right, so in this case, you'll notice that this is under post-processing. And once I type in the post command, it generates this list of arrays that I have over here. So R refers to the translational coordinates. The size of this array is given as nt by nb by 2. So what does this mean? The number of time steps. In my case, I'm working with 30 time steps, so it's 30 by the number of bodies. I have a single body, so it's 30 by 1 by 2. The reason for the 2 is that the coordinates arrays contains the x and y coordinates. So 1, if I specify the last element as 1, it refers to the x coordinates. If I specify the last entry as 2, it will refer to the y coordinates. RD is simply the translational velocity, so the same size as the translational coordinates, also x and y velocities. Then I have the x and y accelerations in RDD, and then P, PD, and PDD are then the rotational coordinates, velocities, and accelerations, and they have a form number of time steps by the number of bodies. So in our case, it will be 30 by 1. And then if I'm interested in the actual coordinates or the velocities of specific points, then I can use RP or RPD. So this is the number of time steps by the number of points by 2, once again for the x and y coordinates and velocities. It also generates the Jacobian matrix, so the number of time steps by the number of constraints that I specify by NB3. So NB3 is simply 3 times NB, and this has to do with the number of degrees of freedom that each body has. Furthermore, I have the Lagrange multipliers, which is the number of time steps by the number of constraints that I specify on the system. And then Eng is simply the number of time steps by 3, so this is the energy. And the 1, 2, 3 elements specify the kinetic, the potential, and the total energies. Right, so in my case, I'm perhaps interested in, let's say, plotting, let's perhaps first have a look at what happens to the angle of the pendulum rod. So I'm going to start off by typing in plot. And then my first entry is going to be what I want to plot on the x-axis. So it will be t. T refers to the time steps. If I scroll down, you'll see over here in the workspace, I have t. It's a 31 by 1 dimension, so a number of time steps by 1. Previously, I said it was 30 by 1, but it's actually 31. You have to compensate for the first, for the first time step as well, or the initial time as well. So it's actually 31 by 1, but that is the number of time steps that I have. Then the y, or what I want to plot on the y-axis will then be the angle of the pendulum rod. So I'm going to type in P, and if I have a look again at what the form of P looks like, it's a 31 by 1 matrix that I have. So the number of time steps by the number of bodies, I'm only working with a single body, so I can technically type in over here P. I want to plot it for all times. So in that case, I use this colon over here that shows everything in that row that I want to plot, comma 1. So for body 1. And then I can perhaps just give it a line specification as well. So let's say I want to plot it as a black line. I can close my parentheses and I can hit enter. And this is then the result that I get for the angle that I'm stepping through. Okay, so it starts over here at, it seems minus 0.5 or somewhere close to minus 0.5. If I perhaps do a quick calculation, if I say minus pi over, what was the initial angle? I think it was minus pi over 6, if I'm not mistaken. Then I get minus 0.5236. And it seems that in this case, I do indeed start off with minus 0.52 or 0.53. So this seems correct. The only problem that I have in this case is that the data is poorly discretized. So it's very coarse data points that I have available over here. And that's why I get these sharp edges over here as well. So if I want to improve that, I've now completed the animation. So I can essentially rerun the DAP simulation just with a finer time point. So I'm just going to say again, clear all. If I hit the up arrow on my keyboard, it will populate with the last command that started off with clear all. So clear all, close all CLC. I hit enter, and now I can run through the DAP again. So which folder contains the model PR_B. I want to correct the initial conditions, yes. I still want to use a final time of 3 seconds, but now I'm going to use a reporting time step of 0.01 seconds. It's going to run again for the same number of function evaluations, which is fine. And now I go directly over to post. And now if I start off typing in PL, hit the up arrow, it will populate the command again. So if I now plot the graph, I essentially end up with these results over here. Okay, so I do see the oscillatory effects of the gravity on the pendulum rod. I don't really expect a decrease in the amplitudes because I don't have any resistive forces acting on the system. So this constant oscillations, constant frequency and periods gives me more confidence in the results that I now got over the time range that I specified. Okay, so a few other things that you might want to plot is, let's say the X and Y coordinates against each other for this system as well. So to do that, I can say plot, then I'm going to plot the X coordinates. So I'm going to start off with R. It's a 301 by 1 by 2 matrix that I have. So I'm going to plot it for all time steps for body 1, and I'm interested in the X coordinates. So my last entry over here will be a 1. Then on the Y-axis, I want to plot the Y coordinates. So that would be R for all time steps for body 1, and now in the 2 direction or the Y direction. And I can once again use, let's say, a black line, or yeah, let's maybe rather do black dots in this case. Okay, and this is more or less what I get. It seems to be, in this case, parabolic in nature, but that is simply because the axes have been scaled, and they are not equally scaled. So if I want to improve my results so that I see this sort of semicircle profile that the system is following, I can simply say axis equal, and then this seems to show a better resemblance of the results that I get. Right, so now jumping into the reaction forces, which are associated with the Lagrange multipliers. I see that the form of the Lagrange multipliers is 301 by 2. So this makes sense in the sense that I have 2 constraints that I specify based on the revolute joint. The revolute joint limits motion in the X and Y directions. So 301 by 1 will refer to the X reaction forces, 301 by 2 will refer to the Y reaction forces. And if I want to plot this, I can simply say plot, and let's maybe plot them as a function of time. So I'm just going to start with T, Lagrange multipliers over all time steps, 1. So that would be the X reaction forces, and let's do perhaps a red line for that. And then I can type in comma. I start once again with my next X definition, and now it's going to be Lagrange multipliers for all times in the 2 direction or the Y direction, and this can be a blue line as well. All right, so if I just have to remember to perhaps add, okay, so I think I just skipped over here one of the commas. So if I add that in, just have to get rid of one of these parentheses as well. Let me add it in again. Okay, so I think the problem over here is just, yeah, so just adding in an apostrophe to end off the line specification. Okay, so in this case, I can now see what my X and Y reaction forces are. If I look at the X reaction force in this case, at the starting point, it seems to be around 6.25. And then the Y value is minus 8.31 perhaps, or somewhere in that range. If I look back at the validation calculations or the hand calcs that I did, I indeed started with minus 6.37 and 8.58. In this case, the signs are just reversed, and this is simply because of the IP and the JP indices that I specify in the revolute joints. If I flip them over, well, I can essentially get the different signs, or I can use the Jacobian matrix and extract the specific sign from the Jacobian matrix, multiply that in, and I should get the correct sign convention in any case. We'll look into that a bit later on, but it's just important to note that from a magnitude perspective, the results that I get over here correlate well. If I perhaps don't want to use the graph to get the initial values, I can also simply type in, LAM 1. So that gives me 6.37, and I can also type in LAM 12. So this is at the initial time step in the X and Y directions, the reaction forces, and I get minus 8.58. And this indeed correlates with what I got over here from my hand calcs. Okay, so in this sense, you can essentially go and play around a bit with the different outputs, and you can go and plot them and see what happens to the system. I'm perhaps not going to spend too much more time on PR_B. I now want to delve into PR_D, and this is now the driven pendulum rod that we're going to consider. Okay, so to do this, I'm going to head back to tab BC12, models, and under PR_D, you'll see there's a driven pendulum rod kinetics file as well. If you open that one, this is essentially the calculations that we did for the case where we have a driven pendulum rod. And we start off now with, once again, the same property. So the mass remains the same, the moment of inertia remains the same, the length of the pendulum rod remains the same. The only change is now we specify some angular acceleration on the system, 2 pi over 60 radians per second square. If I integrate this once, I get 2 pi over 60 multiplied by t plus some sort of a constant. I still assume that my system starts at rest. So phi dot 1 of 0 must be equal to 0. That means the constant value that I get from my integration is going to be 0 for phi dot 1 t. And I end up just with 2 pi over 60t. If I integrate once more, I end up with pi over 60t squared plus another constant. And in this case, phi 1 at time 0 must be equal to minus 30 degrees, or in terms of radians, minus pi over 6. And if I substitute this in, that constant value becomes minus pi over 6. And this is essentially how I define my driver function. So phi 1 as a function of t is then pi over 60t squared minus pi over 6. X1 at time 0 and y1 at time 0 is simply the starting coordinates for the center of mass of the pendulum rod. This is the same as what we got for the undriven pendulum rod. And then I can also go and do a moment equilibrium calculation to find what the moment over here is that would equate essentially to this 2 pi over 60 radians per second square angular acceleration. So I enforce some moment which is equivalent to the angular acceleration. And what I then get is N is equal to 5.1226 Newton meters. If I go and calculate as well the reaction forces in the xi and eta directions, these are the values that I get, and I can once again relate them to the x and y or the global coordinate system, and these are then the values that I end up with that I can use as a validation for my DAP-BC calculations that I do. Okay, so in this case, I'm then going to open up PR_D. just opening up all of its input files. And I just have to close the ones for the previous example that we did. Okay, so if I look at in bodies, this essentially remained exactly the same as what I had for the undriven pendulum rod. All of the the starting properties remained the same. In this case, I just commented out this b1.rd simply because the system is in any case going to use the default value of 0, 0 if I don't specify it. For the endpoints, it also remains exactly the same. So I have 3.2 of the point 1 is specified on ground, points 2 and 3 are specified on the pendulum rod. In joint is now still the revolute joint, so I don't enforce any other joints at this stage. In U vectors is still an empty vector that I have over here. In functs, I'm going to leave open for now. And the reason for this is I've now calculated a torque, which I assume to be equivalent to whatever the angular acceleration is. But you'll remember that the torque that I calculated is actually a function of the starting angle. My question is, what would happen if I just apply a constant torque in this case? So I apply either a constant torque of 5.1226 Newton meters or something higher than that. I essentially want to see what happens to the angular acceleration of the system if I were to use a constant torque throughout. So in funct is going to be an open list at this stage. In forces is now going to change. So I still have the weight force that is acting on the system, but now I also specify S2, still a force structure. Dot type is now T, so this means I specify a torque. And for a torque, I need to specify two things: the body index, so the body on which the torque is acting, and also the magnitude or the actual value of the torque, which includes the sign as well. So positive for counterclockwise, negative for clockwise. So in this case, I'm applying a counterclockwise torque of 6 Newton meters to the system, and I want to see what's going to happen. Okay, so if I just go to inanimate as well, you'll also notice that I've just increased my bounds a bit. So it's now minus 0.75 to 0.75 in the x direction. Y is now minus 0.75, and now I actually expect the pendulum rod to rotate essentially counterclockwise, so it might actually go above the x-axis. So in this regard, I can then run dap, which folder contains the model. In this case, it will be pr_d. And do I want to correct the initial conditions? Yes. I'm going to use a fairly small final time. I'm going to use, let's say, 2 seconds. And I want to run it 0.1 seconds. So I just want to see once again what happens to the system from an animation perspective. So it took 450 function evaluations. If I run anim, I can now see indeed the system does seem to rotate. So it started off fairly slowly, but then at the end it quickly picked up acceleration, or it started to accelerate significantly. If I just want to plot this again, I'm going to say anim, and there you can see the sudden and elaborate acceleration of this pendulum rod. Okay, but now the reporting time step is still coarse, so I just want to now go back and actually start plotting the results. So I'm just going to run dap again, pr_d. Yes, I want to correct the initial conditions. And let's do 2 seconds again. I'm just going to use 0.01 reporting time step in this case. And I can type in post over here as well. All right. Okay, so to perhaps alleviate some of the post plotting that we can do, I've also compiled this script over here that you can use that essentially plots 7 figures with different properties so that we can see what actually happens to the system. Figure 1 plots the x and y coordinates against each other for the position of the pendulum rod's center of mass. Figure 2 will then plot the coordinates, so the x and y coordinates as a function of time. Figure 3 then plots the reaction forces associated with the pin joint. Figure 4 is then the accelerations as a function of time for the center of mass of the pendulum rod. Figure 5 is simply the angle of the pendulum rod. And then figure 6 is going to be, this will be the applied torque, inverse dynamic analysis torque. So these things we're going to look at, I think, for PR_E, which we'll look at in just a moment. And then lastly, figure 7 is the angular acceleration as a function of time. And this is one of the important things that we want to look at. What happens to the angular acceleration if I assume that a constant torque simply acts on the system? Right, so I'm simply going to type in over here post_plot. And now you'll see it generates all of the different figures. All right, so starting off with, let's perhaps have a look at figure 1, which is the coordinates of the system. This is more or less as expected. We can indeed see that the pendulum rod is now following a full circular rotation, and it's making a bunch of revolutions due to this applied torque to the system. There are some discrepancies over here, so you'll see there's double lines. This is simply due to the resolution that we use on the system. Since 0.01 might still be a bit of a coarse discretization of the time, we essentially get these double lines over here. And we also have a very elaborate or spontaneous increase in the angular acceleration. So this also causes the points and the distance between the points to be interpolated more coarsely. But overall, this is more or less the result that we expect to see. Then if we look at figure 2, for the x points and y points, once again, their coordinates are shown over here. We can see as time progresses, the frequency increases for the x and y point deviation over here. And once again, this is as expected. We see an angular acceleration increase, so we expect the frequency of the x points and y points to oscillate more rapidly. Then if we look at figure 3, and I just have to remind myself, figure 3 is essentially the reaction forces that we look at, and also the resultant reaction force. So this is simply the square root of fx squared plus fy squared for that revolute joint that we plot as the third line, which is shown in black over here. Once again, we can see the effect of that torque causing more elaborate oscillations of the reaction forces and the frequencies to also increase. For figure 4, we then have the translational accelerations. And this is quite interesting to see that although, well, in this case, we apply a torque, a constant torque, it doesn't necessarily mean that we're going to get constant acceleration in this system. In this case, we actually see exactly the opposite. We see that there is oscillation in the translational acceleration, which becomes more elaborate due to the effects of torque on the angular acceleration. And then figure 5 is simply, I believe this is the angle then of the pendulum rod. So this is simply an additive angle. It's not going to oscillate between 0 and 360 degrees. It's just going to continue for each revolution to add 360 degrees to the system. So that's why we see a constant increase in the angle or the orientation of our pendulum rod. And then lastly, the rotational acceleration of the pendulum rod for the applied torque only. So the case where we don't have a driver constraint that we specify, only an applied torque, we can see that the angular acceleration is indeed now oscillating as well. We don't have a constant angular acceleration. Okay, so Now we can essentially jump into PRE. And what I'm going to do for PRE is essentially consider, let me just open up all of these files as well. I'm still going to apply the torque of 6 Newton meters. But what I'm also going to do in tandem with this is to define the actual function which is placed on the angular acceleration of the system. So in animate remains the same. In bodies remains the same as what we had for the previous two pendulum rods. In forces, I still apply that torque over here as 6 Newton meters. In funct is now the file that I have to update. And in this case, I have to specify the actual function that I derived over here. So phi1 as a function of time is equal to minus pi over 6 plus pi over 60 t squared. If I go to the user manual and I head to the in funct section over here, let me just check. I think it's, yeah. So over here, it essentially tells me the different ways in which I can define a function, depending on the coefficients that I have available and depending on the order of the polynomial that I want to specify. So I have type A, type B, and type C. Each of these function types also have their own inputs that I essentially have to give. So for type A, I have f is equal to c1 plus c2t plus c3t squared. If I specify a function as type A, I simply have to give the coefficients, so the c1, c2, and c3 values in that consecutive order. If I have a type B function, I need to specify t start, f start, t end, and f end. And this is in accordance with these function curves that I have over here. Type C is then if I have c1 plus c2t to the fourth plus c3t to the fifth plus c4t to the sixth. And over here I need to essentially give it some a sort of a derivative parameter as well, together with the t start, f start, and t end. But in our case, we are essentially going to focus on function type A. Why is this? Simply because if I look at my phi1 as a function of t, I indeed have a parabolic function over here. So I can specify c1, which is minus pi over 6. c2 is what is in front of t. In this case, it's 0 times t, so it's 0. And c3 is then pi over 60. It's whatever's in front of t squared. So if I specify this under in funct, I initialize this function as a function structure. f1.type is a, and then I simply give the coefficient values over here. And you can go and calculate these values. They should correspond to the minus pi over 6 and the pi over 60 values. And then I simply group all of that together under the funct list as well. Then I just have to remember that I have to update my in-joint file as well. I've now specified what the driver function looks like. Now I need to actually say what type of driver I'm working with. And in my case, it's going to be a relative rotation driver. And this is simply because I have an angular acceleration, and the final equation that I get over here is then related to the actual angle or the rotation of the system. So how do I get this? I simply go to in joint, and you'll see the last two entries that I have in this table over here refer to actual drivers or motors that I specify on the system. Relative rotation is a rotational motor or actuator that requires an analytical function, and relative translation is then a translational motion that requires an analytical function. In the case of the relative rotation driver, I need to specify the body on which, or the body between which the relative rotation driver are acting. So IB index, JB index, and then I have to give the index of the function as well. Right, so how do I do it over here? IB index is going to be body 1, so the pendulum rod. The relative rotation driver acts between the pendulum rod and ground, so IB index is 1, JB index is 0, and then the index of the function is 1. If I go back in funct, so it's going to be index 1, which corresponds to f1 over here. Okay, so that I then specify as a joint structure, and I simply add this to my joints list that I have over here. Other than that, in points and in u vectors essentially remain the same as well. Okay, so the important thing to note over here is I now have two combined dynamic analyses that I'm running. I'm providing a constant torque on the system, but I'm also providing a driver constraint which limits the angular acceleration of the system. So let's now see what happens to the results. If I type in DAP, I'm going to say I'm now working with PR_E. Yes, I want to correct the initial conditions. The final time I'm going to make it a bit longer, so let's use 30 seconds in this case, and a reporting time step of 0.1. It now ran for 1,200 function evaluations. So now I can quickly do an animation and see what happens to the system. All right, and you can already see from the fact that I'm using a final time step of 30 seconds, the motion of the pendulum rod is already significantly slower to increase than what it was when I had a constant torque on the system. So something tells me that there is an effect of the driver constraint even in the presence of this constant torque. Now, if I, let me perhaps do, I think I'm going to leave the results as is, see if 0.1 reporting time step is fine enough. But I can now just type in post. And now I just want to go to my post plot over here. I'm going to uncomment figure 6. And I can now run post plot and see what happened to the results. All right, so starting once again with figure 1, I see once again I follow that circular profile that I expect when I have a pendulum rod that is rotating under a certain driver force. So that seems to correspond. Figure 2 now once again shows that I have an increase in frequency for the x and y center of mass coordinates as time progresses. This is as expected due to the angular acceleration of the system. Then I also have over here the Lagrange multipliers related to the reaction forces. So, or the revolute joint rather. So in red, I'll have the X reaction force, Y reaction force in blue, and then I have the total reaction force over here in black. Figure 4 related to the translational acceleration of the center of mass of the pendulum rod. So once again, I can see an increase in the amplitude, an increase in the frequency, and a decrease in the period due to the angular acceleration of the system. The angle also continues to increase. This, what I can perhaps see over here as well is that it seems to be more of a parabolic function that is being followed over here for the increase in the angle of the pendulum rod. So this already gives me confidence that phi 1 as a function of time, that driver function that I specified over there, seems to correspond to the parabolic nature of the function definition. But to perhaps better illustrate what is happening from a dynamics perspective or from a force perspective to the system, I can essentially go and plot the applied torque, which I know is 6 Newton meters. I specified this under the in forces folder or file. Then I also have an IDA torque, or an inverse dynamic analysis torque. This is essentially, if we zoom in on figure 6 over here, the inverse dynamic analysis torque is that reaction or Lagrange multiplier that I get from the driver constraint. So Lagrange multiplier 3 essentially corresponds to the torque that is caused by the relative rotation driver that I now specified. And if I simply add these two, the applied torque and the IDA torque, up with one another, I will essentially get this curve over here, which then oscillates between, it seems, between 6 and -6 Newton meters for the torque. So what this essentially tells us that the IDA torque essentially composes some sort of a braking torque, where previously I had an angular acceleration which continued to oscillate due to the constant torque. In this case, the system says, well, I have a driver function that I need to meet. I need to maintain an angular acceleration of 2 pi over 60 radians per second squared. So in order to achieve this, in light of the torque that is being applied to the system, I need to apply a braking torque so that when the angular acceleration attempts to go above the 2 pi over 60 limit, I can brake it and make sure that it essentially remains at that constant level. And this is also then evident from our last graph that we have over here, which is simply the rotational acceleration of the pendulum rod. It's specified as just below 0.105. If you go and calculate this value over here, you should get, I think, 2 pi over 60 radians per second squared, which is exactly what we specified as an input, as a driver function to the system. Right, so the important thing over here is to notice that BC is very powerful in the sense that it can actually accommodate combined dynamic analyses, and it can essentially compromise between a very extensive load that attempts to break the driver function. It can compensate in the sense that it has some braking reaction forces in that sense. So you essentially remain at the constraint that you specify, the driver function that you specify. Right, and all of this is handled internally. So the Lagrange multipliers that you get already account for these braking forces. You just need to go and interpret them correctly accordingly. And that was essentially the focus then of PR_E, doing a combined dynamic analysis and seeing what the effects are from a braking performance perspective. All right, I think that was quite an elaborate overview then of our first two examples that we looked at regarding the pendulum rod. We still have PR_F to do, which we will look at in the next lecture. But this was essentially the fundamentals of looking at the pendulum rod. So we just wanted to start off with an undriven case, see what happens, then see what happens if we deliberately choose a constant torque to act on a system, even though we know that there is going to be torque deviations. And then lastly saying, well, let's now combine the analysis and see what the effect is going to be on the driver function at the end. Are we still going to meet the requirements that we specified at the start, even if we had certain torques or forces that contradict our motion? Okay, so in that regard, are there any questions before we end the session? Right, so if you have any questions, feel free to raise your hand or type it under the chat messages. I think from my side, it was a bit of a longer session now, but we did have a lot to cover. So yeah, do feel free to have a look at the lecture video as well when you have time and work through the lecture material on your own. You have all of the models available. So do play around with them and see what happens if you change the torques and you, let's say you perhaps use a 4 Newton meter torque instead of a 6 Newton meter, what will happen to the system? And yeah, just start playing around with the parameters and get comfortable with using DAP BC before we jump into the more intensive examples. All right, I think I'm going to give a few seconds for anyone that still has a question. All right, I seem to not see any chat messages, so I believe everyone is happy at this stage with the examples that we did. So in that case, thank you very much, and I'll see you next week for our next lectures on the application examples. Thanks a lot.